Hello class, today what we're going to talk about is simplifying radical expressions. So we're going to have some lovely square root stuff and we're going to simplify it, make it a little bit prettier. So we've got two properties of radicals that we're going to talk about. First, the product property. The nth root of a times b. This is the same as the nth root of a times the nth root of b. And a lot of the times we're going to take it the other way around. So for example here we have the cube root of 4 and the cube root of 2. Since the index here is the same, we can take it and we can multiply the radicands together. So 4 times 2 is 8, so this is the cube root of 8, 2. Quotient property works the same way. The nth root of a divided by b is the nth root of a divided by the nth root of b, provided that b is not 0, because you can't divide by 0. And again, a lot of times it works, but you'll see it more useful going the other way. So here we have fourth root, the indexes are the same, so we can just divide the radicands. 162 divided by 2. So the fourth root of 81, which is 3. Right? And so that's how that works, and that's not too bad. So let's take a look at these. We need to simplify this. Well, notice the radicand is different, but the index is the same. So they're both cube roots. We can take the 12 and the 18, and we can multiply those together. And 12 times 18 is 216. So this is the cube root of 216, which is just 6. Right? On question B, we have the index, again, the same, both fourth root. So that means we can take the radicands, 80, and divide it by 5. So 80 divided by 5 is 16, and the fourth root of 16 is 2. So not too bad. Actually, that should be positive or negative 2. So let's take a look at this. This is a little bit different. This is where they're taking it and they're breaking it up. Okay? And what we do with A, we have the cube root of 135, is we split that up into the cube root of 27 times 5. And the reason we do that is because 27 is a perfect cube. Right? So this is the cube root of 27 times the cube root of 5, just like that property we had back there. And the cube root of 27, well, that is 3. So this is 3 times the cube root of 5. Now, if you're like me, you don't see 135 and think, oh, hey, that's a multiple of 27. I can do. Yeah, don't do that. So what I do is I do this lovely little prime factorization tree. Okay? 135, I look at that and I see 3 times 45. That's what I see. And so I split that out. Well, 45, that's 9 times 5, and then 9 is 3 times 3. Now, these are all cube roots, okay? And we've done this before with squares, and then we were looking for squares and pairs, right? Well, here we're looking for things that are perfect cubes, since this is a cube, or we're looking for 3 of a kind. And so I look at this and say, oh, I have 3 cube roots of 3, right? And then I have this cube root of 5 left over. Well, the cube roots of 3 times the cube root of 3 times the cube root of 3, that's the cube root of 3 cubed, which is just 3, and then the cube root of 5 left over just gets stuck onto the end. All right? And so that's how I do it, because I don't always see factors that are perfect cubes. Part B. Here, we don't like having the radical in the denominator, but we also don't like having fractions in the radical. All right? So I'm not going to just call this the fifth root of 7/8 because then I would have a fraction in my radical and I don't want that. But I can't simplify it, so here's what we'll do. We take this and we need to get rid of this fifth root of 8. So to do that, we're going to multiply by the fifth root of 4, which gives us the fifth root of 32. Okay, and you multiply the bottom by the fifth root of 4, you multiply the top by the fifth root of 4. And now you're thinking, where did that fifth root of 4 come from? All right. Well, what this is, we need to have a perfect fifth in the denominator. And so we could say, well, 8, we want the 8 to the 5th, so we need to multiply by 8 to the 4th. That's really big. And then we're probably going to have to simplify that somewhere. So instead, what we do is we're going to get 8, that's 2 cubed. All right? And then I've already got 3 2's, I only need 2 more. So I just need to multiply by 2 squared, and that'll give me 2 to the 5th. Well, 2 squared is 4, and 32 is 2 to the 5th. So what this is the 5th root of 2 to the 5th, which is just 2. And up here we have the fifth root of 28. And so that's how that works. And that could be a little bit weird, but it's not too bad. Okay, so let's take a look at this. This is the last thing we're going to do, and then we're going to do some examples. So we have 1 over 5 plus the square root of 3. Now, again, we don't like having square roots in the denominator of our fraction. It's no good. So we've got to get rid of this. And what we do here is we use the conjugate. If you remember, we talked about imaginary conjugates, the complex conjugates, and we've had irrational conjugates before. And so the conjugate of 5 plus the square root of 3 is 5 minus the square root of 3. And so that's what we're going to do. We're going to multiply the numerator and the denominator by 5 minus the square root of 3. And the reason for this is now we have that a squared plus b squared difference of squares, right? A squared minus b squared. A plus b, a minus b, right? So when we multiply those together, we get 5 squared minus square root of 3 squared. And then we've got to multiply the top two, so that's just 1 times 5 minus square root of 3. Well, 5 squared is 25. The square root of 3 squared is just 3, so this is 5 minus 3, or 25 minus 3, so that's just 22. And we distribute the 1 in, and there's 5 minus square root of 3. So you see, no more square roots in the denominator. We do have them in the numerator, but that's okay, as long as they're not in the denominator. That's the important thing. So here we go. These are a lot easier. Not a big deal. I have 4th root of 10 plus 7 4th roots of 10. Well, notice our radical is exactly the same in both times. I have 1 here and I've got 7 there. We just add them up and that would be 8 4th roots of 10. That's all that is. Same thing here. We have 2 8 to the 1/5 plus 10 8 to the 1/5. So that would be, well, 2 of them, and there's 10 more of them, so that's 12 8 to the 1/5. Not a big deal. See, a little bit trickier here. We're going to want to do that little factor tree and simplify this cube root of 54, because notice our radicands are different, so we can't just combine them. And, well, 54, that's 27 times 2, and 27 is a perfect cube. So we can just do that. 27 times, cube root of 27 is 3, so this is just 3 cube roots of 2. So now I've got 3 cube roots of 2 minus 1 cube root of 2. This one here, right? Well, 3 minus 1 is 2, so I've just got 2 cube roots of 2. All right? Okay. So here we go. Here are 8 examples. I want you to pause the video, see if you can come up with the answers to these, and then come back and we'll see how you did. Alright, let's see how you did. And there they are. Aren't they lovely? If these are the answers you got, you are awesome. You got them all right, and you're good. You're done with the video. Congratulations. If not, then we need to figure out what went on. So let's start with number 5. Number 5, let's see. We look at this, and they have the same index, so we can multiply the radicands together. So 27 times 3, which is 81, and the 4th root of 81 is 3. Okay. So let's look at 6. Okay, 6 again has the same index. The radicands are different, but that's okay. The index is the same, and 250 is divisible by 2, so we can just divide those out. And 250 divided by 2 is 125, and the cube root of 125 is 5. All right, on 7, let's see here. We need to simplify this 104, so this is going to be the factor tree. If you can't see, oh, this is obviously a divisible by whatever perfect cube that is, and I don't know, so I'm going to do the factor tree. So we have this. Well, 104, that's divisible by 4, and so we have 4 times 26. Cube root of 4, the factor there is 2 and 2, so we got cube root of 2, cube root of 2. 26, that's 2 and 13. Hey, I've got 3 of a kind. I've got 3 cube roots of 2. So that 2 comes out of the radical, and so I have 2 cube roots of 13. Number 8. Well, 3/4 doesn't simplify. So we're going to have to multiply and get rid of this 4 here. All right. So what we do, well, 4 is, this is the 5th root of 3 over the 5th root of 4. 4 is 2 squared. I've got 2 2's, I need 3 more because I need to have a perfect 5th. So I'm going to multiply numerator and denominator by the 5th root of 2 cubed. Alright, so on the bottom, I have the fifth root of 2 to the fifth. Right, or you could put 32, that's fine. On the top, let's see here, 2 cubed, that would be 8, so I've got 3 times 8, so that's fifth root of 24. And down here, the fifth root of 2 to the fifth is just 2, so that's where that comes from. Right. Number 9. Number 9, we have this complex thing here. So what we're going to do there is the conjugates. So the conjugate of 6 minus the square root of 2 is 6 plus the square root of 2. Multiply the numerator and denominator. Well, on the bottom, we're going to do that first because it's the easy one, right? So we have 6 squared minus square root of 2 squared. On the top, we have 3 times 6 plus square root of 2. It's going to look like that. So the numerator, we needed to distribute that in. So 3 times 6 is 18. 3 times square root of 2 is 3 square root of 2. And here we have, well, 6 squared is 36. Square root of 2 squared is 2. So this is 36 minus 2, which is 34. Right. 10, everybody should have gotten 10 right. This is 7 fifth roots of 12 minus 1 of the fifth roots of 12. So it's just 7 minus 1. So we have 6 fifth roots of 12. All there is that. Number 11 is a little bit trickier. We have, starts off really easy, right? 4 times 9 to the 2/3 power plus 8 9 to the 2/3 power. So that's, well, 4 of them and 8 more of them. So that's just 12 times 9 to the 2/3 power, right? Well, we can simplify this. And normally we'll want to take care of the denominator first, the radical, but I don't know what the cube root of 9 is. 9 squared, though, I can do that. This is the cube root of 9 squared. 9 squared is 81. And then I look at this and say, well, 81 is 3 to the 4th, right? I'm taking the cube root of 3 to the 4th, and what happens there is 3 of those 3's can come out because it's the cube root, and I've got 3 of them in there. So this is 3 times the cube root of 3, okay, times 12. You still got a 12 in front. So 12 times 3 is 36 cube roots of 3. So that's where we come up with that. Let's take a look at number 12. Well, number 12, the indexes are the same, but we're adding, we're not multiplying, so we can just add those together. So we're going to need to break up this 40, see if we can do something with that. All right. Well, that 40, that's 8 times 5, but we're looking for cubes, right, because we have a cube root there. 8 is 2 cubed. So we can take that 2 cubed out. You can do it like this, or you can do it in the factor tree. That's fine too. So we have 2 cubed. The cube root of 2 cubed is 2. So this becomes 2 cube roots of 5. So we have 1 cube root of 5 plus 2 cube roots of 5 gives us a total of 3 cube roots of 5. All right. And that is all the different ways and methods and techniques that we can do to simplify radical expressions. And some of them are a little bit tricky, so you might need to watch this again, especially with this one here and getting that radical off the denominator, either here or with the conjugates. Very important about the conjugates, this only works with squares, with the square root. If you have cube root or something like that, you'd have to do something else, and we're not going to be doing that in this class. That's a higher level thing. So, there it is. Hopefully you found this helpful, and I will see you again.